Okay, we're just continuing with the June 2014 M2 Edexcel paper here, starting with question 5, which is a collisions question, a little bit unusual. Talks about a particle which starts off at 0 between two walls, and it's been projected with speed u towards one wall, and the walls are 2 meters apart. So in other words, it starts off 1 meter from this wall. It tells us E, so there's none of the normal kind of setting up equations with E or anything. It tells us E with both walls being the same. So this is going to return with speed 2/3 u with constant speed. And then at the next point, it will return again with 2/3 times that, which is 4/9 u. I'm not needing that for part A, but it will be useful in part B. Okay, so we're going to work with that. First bit's really a very straightforward impulse thing. Impulse is change in momentum. So the impulse is the mass 0.7 times, no, it's not 0.7, that must be a previous question, m times by the initial velocity, the final velocity, which is 2/3 u, minus, now be careful here because it's returning with an opposite sign, so that's 2/3 u. So that gives us I is minus 5/3 mu. So the magnitude of the impulse, because the negative just gives the direction. The negative is because the direction of the impulse it changed it is there, and we're taking that as positive. So let's not worry about the negative. The magnitude of it is 5/3 mu, so lambda equals 5/3. Okay, so let's move on to the next part. The next part, basically what it's saying is, it says the particle returns to O having bounced off each wall once. So basically what's happened is it's gone to here, then it's come back again, returned, and then it finally returns to the wall here. So it's gone there for 1 meter with speed u. It's gone for 2 meters with speed 2/3 u. And then finally for another 1 meter with speed 4/9 u. I did say I was going to use the 4/9 u in this part. Right, I'm now going to set up an equation, but before I do that, remember this is constant velocity here. It's constant speed, constant velocity. And so we've got our normal kind of relationship between these things. Distance equals speed times time, if you like. So if we want the time taken, that's distance over speed. So time is distance over speed. And we're told that this whole journey here, outwards there, then doing this bit, is equal to 3. So I'm going to take each bit individually. For the first bit, before it's collided, we've got the distance travel, the time for that to take is the distance, which in this case is just 1 meter because it's just gone halfway between walls, divided by the speed, which is u, for that part. Then we're going to do this part where it's now 2 meters, and obviously the speed is now 2/3 u. Then we're going to do this final part here, which is again 1 meter, because it's only halfway, going back to the back where it was, times by the new speed after colliding a second time, 4/9 u. And we are told that it's 3 seconds. Okay, so we just need to tidy that up, and that's going to get us our 6 marks, so it's not too bad. 1 over u, that comes to, this comes to 3 over u, the 2 cancels, and this comes to 9 over 4u, which is equal to 3. That's obviously 4 over u plus 9 over 4u equals 3. I'm going to times by 4u. So that will make this first term here 16 because the u cancels. It will make this term here equal to 9 because the 4u cancels, is equal to 12u. So that gives us u is equal to 25 over 12. And that's it. That's that question done. 9 marks done relatively quickly in 5 minutes. Not too bad. A bit disappointed not to have all those multiple collisions, which I quite enjoy, but never mind. We've done it and we can move on. So let's have a look at question 6. Okay, so it's our projectiles question. I've never known a projectiles question to be missing, I don't think either. Anyway, so we've got an unknown alpha for the first part. We're told that the speed at b is 10 meters per second. Whenever we have just speeds involved and we want to get a relationship without worrying about angles, it's a good idea to use energy. So use energy is conserved. So using energy, we have the initial kinetic energy, which is going to be half times by the mass, which obviously we don't know, times by 14 squared, is going to be equal to the kinetic energy at the top plus the potential energy that it's gained here, and that's going to enable us to work out h. So that's m times by g times by h. So we can see m cancels, and then we can work that 14 squared is 196, so that's 98. 150 plus gh. So h is equal to 48 over g. They did accept actually that as an exact answer, but they don't. I'm not really convinced sure when they accept exact things with g in or not. So let's give the answer to 2 significant figures or 3, because they always accept that as well. And that makes h equal to 4.90 or 4.9 meters. Okay, but they did accept the 48 over g as an answer this time. Okay, now part B, we're now given that sine alpha equals 0.85. So it's what wants us to find a horizontal distance. Okay, what I'm inclined to do is, now that we know h, work out the time taken, and once we've got the time taken, we to get from here from A to B, we'll be able to work out what the horizontal distance is. So let's work with that. Okay, so let's just work with v s equals ut plus half at squared. S is equal to we're going to do it vertically from A to B. S is equal to the 48 over G. U is equal to 14 because it's in the initial speed, 14 sine alpha, so that's 14 times 0.85, because we're given sine alpha, 14 sine alpha, so that's that, minus, or times t, minus half g, which is 4.9, t squared. Okay, so that gives us, if we work that out, that's 4.9 t squared is equal to 14 times, so plus minus 14 times 0.85, which is 11.9, and then that's plus 48 over g equals 0. And if we solve that equation, I won't go into the ins out. I presume you can use the quadratic formula. So solve, and we're going to get t is equal to 1.903. The negative one is not relevant. Okay, so 1.903 is the answer there. So, sorry, I didn't mean to say negative. Often we get a negative answer, but we get, in this case, we get two answers, 1.903 and 0.525. But we discount that one, it's not negative, but that corresponds to this point here, where it's h on the way up rather than the way down. So we want the bigger of the two numbers, which is 1.903, to a certain number of decimal places. Okay, so that gives us the time that it takes. Now the distance from A to B, therefore, well, don't forget the horizontal speed is going to be equal to 14 cos alpha. Okay, now 14 cos alpha, you can work out inverse sine and do the rest of it. So you can work out alpha and then cos it. I suppose that's probably the easiest thing to do here. So we can just say the distance AB is equal to the 14 cos alpha and times by the time, which is equal to, let's put time signs, 1.9034 ... Now cos alpha is equal to the actual angle is 58.2. So if I do the cos of that equal to 0.526 when I work in it, so that's 14 times 0.5267 with a load of other stuff times 1.9034, and that makes it equal to, that comes to 14.0 meters to three significant figures. Okay, a little bit fiddly there, but not too bad, really. Yeah, numbers didn't work out nice, but there we go. So let's get on to the next question, question 7. So it's a statics question. It's hinged at A, and I think it gives a symbol. It says that the force at A, the vertical force, is Y. So let's make the horizontal force X to be consistent. And in its first bit, 6 marks, show that that is the case. Now, it's almost always a good idea to take moments about the hinge here. If we do it, note that we've got a W here, and it says it's uniform, it hasn't attached, it hasn't said what the length of it is, doesn't matter, we can call it A or we can call it L, whatever we like, or 2A in this case. Now, if I take moments about A, as I said, Y and X is going to be out of my equation. I'm going to get W in terms of P. Now, if I then resolve vertically, I'll get Y in terms of P. So I'll then be able to substitute. So our two equations are going to be moments about A, which I say, taking moments about the hinge is almost always a good idea. So moments about that, note that the angle here is theta. So the clockwise moment of W is W, and note that note the component here is W cos theta. So it's W cos theta times by the length, which is A, and that is just equal to P times 2A, because the P is already perpendicular to the line of action there, so it's perpendicular distance, which is 2A. So that just gives me P is equal to W cos theta over 2. Surprisingly simple. So now let's just resolve vertically. Said it right, but the wrong thing down. So now let's just work out what the P for us here. Hopefully we can see what the angle is here, because this angle's theta here. Let's try a bit of a better job than that. Because this angle's theta. This angle here is 90 minus theta. This angle here is 90 minus theta, so this angle's theta here. So that angle is theta. So we have, if we're resolving vertically, we've got P cos theta, because it's adjacent, it's next to the marked angle. So P cos theta, kind of reassuring because we want to get a cos squared there. P cos theta plus Y equals W. So all we have to do is now substitute for P. So we have W cos theta over 2 cos theta plus Y equals W. That's going to get us our expression, I think. So that gives you Y is equal to W minus W cos squared theta over 2. I'm putting over a common denominator and taking a W2 out as a factor. That gives us what we want. Okay, done. So now for part B, it's given us that theta equals 45. So we can resolve horizontally now. That gives me P sine 45 equals to X. So that gives me, and we know that P is equal to W cos theta. So that gives me X is equal to, and theta is 45, so that gives me X is equal to cos 45, because I'm basically subbing P into this. So X is W cos 45 over 2 times sine 45. Well, cos 45 is 1 over the square root of 2, and so is sine 45. Some of you are probably thinking, why hell am I doing this? I'm just going to work out on my calculator. Basically, I've come to the conclusion it's W over 4 without using a calculator. And if I was actually thinking this without saying it, I probably would do it much quicker than anyone could write that. So that's W over 4 is X. Now, that's because what we're wanting to find, basically what we want to do is we want to find X and Y, and then we can work out the magnitude of the force because by using Pythagoras on it. So we've got X is W over 4. Now Y we can just pull down from before. So we've got Y is equal to W over 2 minus cos squared 45. Now that's W over 2, as I said, cos 45 is 1 over the square root of 2, so that's 2 minus a half, because it's 1 over the square root squared. So that's W, 3W over 4. So we have basically the X and the Y, and we want the resultant force here, so this we want the resultant force, the magnitude of that force there, which will be X squared plus Y squared. So the resultant force, R, is equal to the square root of X squared plus Y squared. Okay, so that's equal to the square root of X squared, which is W squared over 16. Plus Y squared, which is 9W squared over 16. So that makes it the square root of 10W squared over 16. But of course that can simplify down a bit. We have that as W, the square root of 10 over 4, if we just separate the third out. And that's it. 6 marks for that as well, not too bad. I've seen much worse statics questions than that. It was better than it looked, in fact. Okay, let's move on to the last question. Okay, it's an energy question. We've got something slipping down a slope, and the slope is 25 degrees. And we've got the speed. It's been released from at rest, so it's 0. And then it slides down, V equals to 7. And what else has it given us? It's given us that the distance between these two is 10 meters. It says use the work energy principle, so we better use the work energy principle. As I've said before, I like to express my work energy principle like this. Work done, okay, by external forces. In this case, the only force is the friction. So the work done against friction. So if we can find the change in kinetic energy and the change in potential energy, then we'll get the work done. So change in kinetic energy, well, that's increased. It's gone from 0 to half times, and we're given the mass of the thing, I believe, yeah, half times 5 times 7 squared. And it's lost potential energy. Oh, bad diagram. It's 10 meters down, and we know this vertical distance here, because this angle's 25, we know this vertical distance here is 10 sine 25. But it's lost that energy, so it's take away, because it's reduced, take away the potential energy, which is M, which is 5, times by G, which is 9.8, times by 10 sine 25, equals to, and it's going to give us a minus sign when we work that out, that will give us, just working it out, 84.6 joules or 85 joules. Actually, it's given us a minus 85 joules, and that's because the frictional force is taking energy away from the system. So work done against friction. It's a strange idea really, but basically it's going to be equal to 85 joules or 84.6 joules. Okay. It does say in the mark scheme they expect it to be positive as well, so they want the work done. Can't talk about the work done being negative when you're looking for a final answer. It's negative here because it's taken energy away from the system. Then it says find the coefficient of friction between the particle and the plane. Well, we can actually work out the frictional force easily now. Let's just do that, because we have work done. We're on part B here. Let's separate our questions. We've got work done equals force times distance. So therefore, if we call F the frictional force, that's going to be equal to the work done we found from before, which is our 84.5, the full calculator answer, divided by the distance, which is 10. So that equals to 8.458 blah 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 blah. Okay, so that's our frictional force. Right, so now let's just do a bit of resolving, because we need the reaction force here. We've got the reaction force. It must look the same way. I just did it that way because it was moving down the slope. So the reaction force is there, and the weight of the particle is equal to 5g. We've got the angle here, which is 25. So if we resolve perpendicularly, we get R equals 5g cos 25. Right, so finally, if I write it over here, we've got F equals mu R. So mu is equal to F over R, which is our 8.458 blah blah blah, divided by 5 times 9.8 times cos 25. Okay, so given two significant figures to that answer, I get mu is 0.19. Okay, and that is June 14 completely done. Okay, lots of different aspects, but not too bad as papers go, I don't think. Okay, we're done.